So, welcome to the class which we are doing current electricity again in continuation. Two lectures we have already discussed. So, first lecture we did with the drift velocity and mobility of the charges. Then we spoke about the Ohm's law, the variation of the resistance and resistivity, variation with the temperature and all. Now today we are going to do in continuation only. So our objective is to study the series and parallel combination of resistors. We will be studying the heating effect of current. It means we will be looking for the electric power, electric energy and efficiency of the electric device as well. So combination of resistances, we can combine the resistances. Of course, we may have the carbon resistors, we may have the wire bound resistors. That is not any problem. Any type of resistors we may have, but we can combine them in series or in parallel. Two methods are there to combine the resistances, and that has found many applications at many places, because if we know how we can combine the resistances, then as a result we can use them in different circuits as per the requirement. So first with you is series combination of resistances. Like we are taking three resistances, R1, R2 and R3. Resistances are having the different values of this R1, R2 and R3. When we connect them in a circuit, always we have to give a source, because without source the charge will not keep flowing, they will stop. So this is the bat symbol for the battery. For one cell we simply put one bigger line and a smaller line. If we are putting more than one cell, then it becomes battery, and this is the symbol for the battery. This is the key, which is just like a switch, it acts. Ammeter is always connected in series, voltmeter always in parallel. So what happens when we are connecting these resistances in series, then the same amount of current is flowing through these resistances. But if you see the potential difference across the ends of these resistances, they will come out to be different. Like we are taking for this R1 it is V1, for R2 it is equals to V2 and R3 equals to V3. So what it is that we will be writing the values for V1, V2 and V3 by using Ohm's law only. Using Ohm's law, because most of the times most of the conductors, they are coming under the ohmic conductors. Though non-ohmic conductors, that is we are not doing experimentally, we will be further discussing its applications. As we have discussed in the previous class, we are having two type of conductors. One is ohmic and other is non-ohmic. So according to your syllabus, we have to talk in detail of the ohmic conductors. So they are having the resistances R1, R2, R3. Potential difference across R1, we are calling it as V1, which is equals to IR1, because current is same current I is passing through all the three resistances. Similarly, potential difference across R2, which can be written as V2, it is equals to IR2, and same way V3 can be written as IR3. Now what happens if I the equivalent circuit for this resistances, and this is the equivalent circuit with me. For the equivalent circuit, I am getting R equivalent equals to the V, because V is the potential difference provided by the source, that is the cell or the battery with me. Now V that will be given by taking the sum of all the three potential difference across the three resistors here. So V can be written as V1 V plus V2 plus V3, and if I put the values of V1 V2 V3, then I am getting this V equals to IR1 plus IR2 plus IR3. Now this is one equation, and this is another equation, which is by taking the equivalent circuit. If I compare these two equations, then I am getting R equivalent is coming out to be R1 plus R2 plus R3. And of course, if there are n resistances, then you have to add all the n resistances, and this I may write the equivalent resistance, or the equivalent resistance for the series combination, I may write it as RS also. So that is your choice. You want to write R equivalent or RS, both are equally correct. Now if I connect the resistances in parallel like this, Now what happens? Now the potential difference across the three resistors will be same, but current I will be divided into three parts. This first we will discuss in the coming chapter also, coming lessons about the Kirchhoff law also, that is following the Kirchhoff law. I is getting divided into I1 plus I2 plus I3. So I can write the net current which is to be drawn from the cell can be written as the sum of these three currents, that is I equals to I1 plus I2 plus I3. But potential difference will remain same across all the three because this is in parallel, voltmeter will come in parallel. And then if you find the I1, I2, I3, again you have to use the Ohm's law, and by using Ohm's law, when you are finding the current in R1, this is first resistance with me, R1, then it can be written as I1 which is equals to V upon R1. Similarly, I2 can be written as V upon R2, I3 can be written as V upon R3. And if I put the value of this I1, I2, I3, then I am getting this as the result, or I may take V common. I will be getting inside equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Now again if I go with the equivalent circuit, then I may call this resistance as the equivalent resistance. Then I will be having the circuit again like this, and this from the equivalent circuit you will be getting the potential drop V will be equals to IR, and or you can write I equals to V upon Rp. So on comparing from the initial equation, I am getting it equals to V into 1 upon R1 plus 1 upon R2 plus 1 upon R3. So on comparing, you are getting 1 upon Rp, it is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Similarly, you can write for n resistances, then it will keep on adding the reciprocal of those other resistances plus 1 upon Rn can be written. So these are very simple things. Electrical energy, though not directly in your syllabus, but the questions sometimes are asked on the basis of this. So basic knowledge should be there with you, that energy, it is the ability to do the work, and more work means more energy. When I am talking about the electrical energy, it is defined as work done in moving a unit positive charge through a potential difference of 1 volt. So work done will be stored as the electrical energy. So electrical energy, it is equals to work done, which is equals to Q delta V. Delta V is of course the potential difference, and because it is energy, so units will be joule. Or when we talk about 1 unit of electrical energy, it is 1 kilowatt hour in terms of the power. And of course 1 kilowatt hour you have already done 3.6 in terms of minus 6 joule. So that way the units can be used whenever required. If you want to see the expression for the power and heat produced, this is, we are going to see the expression for the heat produced and the power. Firstly, power with you. If I am supposing that charge Q is taken from one point to another in a conductor, then the work done, it is given by the definition of the potential difference, that is work done in bringing a unit positive charge from one point to another point. So work done can be written as Q delta V. Delta V I may write it as VB minus VA. And what is power? Power is rate of doing the work. It means work done divided by the time taken. So if I put the value of work done, that is Q delta V upon T, then Q upon T, that is charge flowing per unit time, that is current. So I can write it as VI. Then I may take V as the potential difference, I as the current flow. So in general, we write P equals to VI, and of course the unit for the power is watt, and 1 watt it is equals to 1 joule per second. And bigger units we may use kilowatt as per the requirement. And if by using Ohm's law, you know V it is equals to IR. So if you put the value of V equals to IR, then power will become I square R. Or if you put the value of I square, that is in terms of V square upon R square, then 1 R will get cancelled and you are getting V square upon R. This is means all the three formulas can be used for power. One is power, it is equals to Vi or I square R or V square upon R. And if we want to talk about the heat produced to see the heating effect of the electric current, then it is equals to power into time. So like electrical energy also can be written in terms of the heat produced. At times we may write it, then it is given by I square RT or V square upon RT. So unit is joule because it is the form of energy. So energy unit is joule for as far as the SI unit is concerned. But if you want to derive the expression for the instantaneous power of devices, then in series we are getting power 1 upon power equivalent will come out to be 1 upon P1 plus 1 upon P2 plus 1 upon P3. I am not doing in that detail because it is not mentioned in your syllabus specially. But at times if you want to use the formula for parallel, that is equals to P1 plus P2 plus P3. You can keep the things in mind and you can use them directly in the numerator. If I want to talk about the efficiency of the electrical device, then efficiency is the power output to power input. So for 100% efficiency, it is an ideal thing which is not happening in daily life because there are some losses there always. So we can calculate efficiency in percentage, that is given by P output divided by P input multiplied by 100. And when we will talk about the source cell efficiency for the source, that will be given by the potential difference divided by the EMF E, power output Vi divided by power input, that will be the EMF of the cell. Of course, we will be dealing in detail about the EMF and potential difference in the next lecture with you. You may see the applications are there for the heating effect of electric current in day-to-day life, where this heating effect of electric current is used in filament lamps, in fluorescent lamps. In electrical heating also we are using in electric cookers, electric heaters, electric kettles are there, irons are there, and like in thermistors we talk about, which is used as an indicator in electric iron, that is a non-ohmic conductor. So non-ohmic conductors we are finding applications at many places and we will be dealing with those in the coming lectures. This is a question with you for solving for finding the equivalent resistance between 2 points A and B as it is shown in the diagram, and they are saying every resistance is of 2 ohm. So for such questions you have to go with the symmetry. You have to see which resistances are in series, which resistances are in parallel, like here COD, this all 3 points are at same potential. So you will be having these three resistances here, AO, AC and AD. These three are in parallel, and similarly these three are also in parallel, and then whatever result will come, that will come in series with each other. So you will be solving it, these three are in parallel, so you will be finding 1 upon RO, it is equals to 1 by 2 plus 1 by 2 plus 1 by 2. You are getting R across this AO, which is coming out to be 2 by 3 ohm, by simply solving it by taking LCM and adding the things. And similarly, if you find for this BO, this also comes out to be same because the values are same on both the sides, 2 ohm each they have given. So now this and this are in series. So you will be adding these to get the resultant, or you may say the equivalent resistance across the points A and B, that is RAO plus ROB, which is equals to 2 by 3 plus 2 by 3. So result with me is coming out to be 4 by 3, or I may leave 4 by 3 ohm, or I may write it as 1.3 ohm. Both are equally correct. So basic understanding is to how to see the resistances to get the results. And of course they may ask you, they may give you the potential difference, they may ask you to find the current through each branch. That can be the added question we may discuss in the next class, but this is the basic question with you. Next question again on the resistances, we are having method. They are simply putting 6 equal resistances. Each resistance is given 4 ohm now and connected in this form. These two resistances are in parallel about this point CD, and these two are also in parallel like this shown. And this lowermost resistance across AB is coming out like this. So this is the best way to do the things. This resistance which is across CD will not contribute, will remain ineffective, because C and D, they are at the same potential. You may say it will act as a short circuit, it will not contribute to the resultant resistance or the equivalent resistance, because these two are in series, these two are also in series, and then all these three are in parallel. Here if you are doing, then this is 2R, so 1 upon 2R plus 1 upon 2R plus 1 upon R. So you are getting it equals to 4 upon 2R. So 4 upon 2R means this is R by 2. R is given 4 ohm. So R equivalent is coming out to be 4 by 2, which is equals to 2 ohm. This is the question on the color. As I said, now MCQs are there with you. They may give you the numerical problems as MCQ, giving you the options, or they may give you for color coding also. All will be having the equal weightage, 1 mark. So every type of question you should be able to do. Like they are asking what is the color code for 4.7 kilo ohm resistor with 5% tolerance. So 5% tolerance, it means the gold is the tolerance ring that is given in every option. So I will not get any hint from here. Then it is 4.7 kilo ohm. 4.7 kilo ohm means 4.7 into 10 to the power 3. It means 4700. So it means first digit is 4. 4 is the color for this yellow. So it means first color is yellow. So these three options can be there. Fourth option is ruled out of case. Then there are second digit is 7. 7 means violet. Violet is there in C and A. It means either C or A is correct. Then you have to see the power. Power is 4700 means 10 raised to the power 2. 2 is the digit for red. So it means the first option is correct. So you have to take care of the decimal is to be adjusted, otherwise you may end up with the orange color, which will be a wrong option with you. So the first one is the correct option. Getting the point? So this is the correct option with me. Now coming to the second question, what is the nominal resistance of a resistor with a color code brown, green, black or silver? Then brown means 1. First digit is 1 of course. Green color is 5. So brown is 1, green is 5, black is 0. Black is 0 means 10 raised to the power 0. 10 raised to the power 0 means 1. So it means first option again. This will be the correct option with you. And of course they are not giving you plus minus tolerance, they are not giving you, so no need to go for that. Only for brown, green and black color you will be giving the results. Black is 0, 0 means 10, because third digit is to give you the multiplier. Multiplier means 10 raised to the power. 10 raised to the power 0 means 1. One more question with you is here. You can see that a silver wire is there of 10 ohm resistance and is stretched to thrice its original length. You have to find its new resistivity and new resistance. Of course, resistivity is independent of the dimensions, so resistivity will remain unchanged because it is dependent only on the nature of the material or on the temperature. So they are not giving any variation in temperature, so for this case it will remain constant or unchanged. But for resistance you can find, and when I am having the wire is being stretched to thrice its original length, but volume will remain the constant, volume will remain the same. So you can write volume equals to A dash L dash, which is equals to AL, or you can write A dash upon A, which is equals to L upon L dash. So it can be written as, because L dash is 3 times L. This is given in the question, so you can write L dash equals to 3L. So you are getting A dash upon A equals to 1 by 3. And now when you write the ratio of the resistances R dash upon R, it is given by rho L dash upon A dash divided by rho L upon A. So you can put the values for L dash upon L and A upon A dash, which is coming out to be, by taking the product, the result is coming out to be 9 times. So you are getting R dash, it is equals to 9 times the original resistance R, and original resistance is given in the question 10 ohm. So the new resistance you can write, which is coming out to be 90 ohms. So unit you have to must mention at the end, as you know, otherwise it's a question of your marks will be deducted. Even after solving these many things, if you are not writing ohm here at the end, then your mark will be deducted, half mark will be deducted. So this is actually a simple question, but you have to keep this thing in your mind that volume will remain the same. So then you will be able to work out with the things. One more question is there with you, where the heating effect is there, or change in temperature I can say is there, that they are saying a nichrome heating element which is connected to a 220 volt supply. 220 volt is actually for AC supply only, because these devices they work with AC. But for the temperature coefficient, the formula we have done earlier, so that will remain the same. They are saying a nichrome heating element connected to a 220 volt supply draws an initial current of 2.2 amperes, which settles down after a few seconds to a steady value of 2 amperes. So initial current is 2.2 ampere, and then equilibrium or stable current you may say is 2 amperes. Room temperature is 30 degrees Celsius. And average temperature coefficient of nichrome is given, that is 1.7 in 10⁻⁴ per degree Celsius. So you have to find the final temperature where it is getting this final current, that is 2 amperes. So what it is, this I1, I2 is given, V is given, alpha is given to you, and initial temperature is given. You have to find the final temperature where it settles down. So you will find the resistance at the room temperature, which is V upon I1, by using Ohm's law only, and you are getting it equals to 100 ohm, which is I am calling it as R1. R1 is at the room temperature T1. Similarly, at the steady temperature, you are getting V upon I2, which is 220 upon 2 means 110 ohm. I am calling it R2. This T2 is to be calculated where it attains the stable or stability, I may say. Then this formula for coefficient of your temperature coefficient of resistivity or resistance, here we have to use it for resistance. So I will be writing it as R2 minus R1 divided by R1 into T2 minus T1. So from here you can calculate T2 minus T1 by simply putting the values of R2, R1, R1 and alpha. All the values are there with us. So you put the values, and when on working out, we are getting T2 minus T1 is 588 degrees Celsius. And from here you can calculate T2, which is coming out to be 588 plus T1. And T1 is 30 degrees Celsius. So you can put the value of T1, which is coming out to be 588 plus 30, which is equals to 618 degrees Celsius. So this is the final temperature where it settles down the steady value of the current. And then of course when we use the formula, otherwise we write R1 minus R0. So whatever according to the question, we can take the values and we can work out with the things. This is our suppositions, and the question is not very difficult, but of course you should be able to remember the formula for the temperature coefficient for resistance. Similarly, the question can be on the resistivity. Thank you everyone.